Hi guys, I am standing here in Uppsala, outside the cathedral, with astrophysicist Andreas Korn. You describe yourself as a space archeologist on your website.
Yeah, something like that. A stellar archeologist.
Stellar archeologist.
Yeah. So space. So there's a distinction between astrophysics or astronomy and space physics or space science. And space science is something where you can send probes.
Yeah.
So it's essentially the solar system. So we here in Uppsala have a department where we collaborate between the astronomers and the space physicists because we have a branch of the Swedish National Space Physics Institute here in Uppsala. But so the astronomers cover everything outside the solar system, and the space physicists do planets and the sun and the solar wind and the comets and asteroids and whatnot.
Okay.
So archaeology is, but it's true. Archaeology is my topic. Yeah, in space. And it's about the evolution, the long-term evolution of the Milky Way in particular, because the Milky Way is the stellar system that we're part of, and we can study in the greatest detail. So it's the one galaxy we can really study inside out.
Did you always know that you would end up in sort of like academia or doing what you're doing?
I guess I knew by the age of 12 that I would want to become an astronomer, yes. One key event was going to a planetarium for the first time in my life.
Yeah.
Which was, I don't know, I cannot pinpoint, it was during a summer vacation in northern Germany. But it must have been around, as I said, when I was 11 or 12. And that was just an eye-opener for me, and I was so fascinated. I mean, it's only a simulation of the night sky, but then I did what every amateur astronomer would do, and I mean to ask my parents to get me a telescope for Christmas, and I started to explore the night sky whenever I had time, and whenever I felt I could wake up. I mean, that's of course sometimes not so easy. And I discovered Saturn by myself, without knowing that it's there that very night. And that's just mind blowing.
Yeah, when you see the rings.
Yeah, exactly, for the first time, and you see it live. I mean, that's just something that, we have much better imagery, of course, now with the probes that we have sent to Saturn. But seeing it live is still a wonderful experience. Wow, how vast is the cosmos, and at the same time, how little am I? And at the same time, this feeling of, wow, I'm part of this.
Yeah.
So it's a bit of both. It can make you feel very small, but also make you feel, kind of taken care of in some cosmic way. Yeah. Which is really cool. Give you an idea of the whole field. So use stars as traces of how the galaxy looked at any time in history. So let's say you have a star in front of your lens, in front of your telescope, and then you take a spectrum. The spectrum encodes what it is made of. Yeah. That's what you want to observe, that's what you want to model and measure. And then you also, as I said, have to put some age on it, and then the galaxy was in this stage of evolution when this star was built.
Okay,
that's the basic idea.
So depending on what stars are made, the elements it's made of.
The elements, that's right. Yeah.
That will determine when it was made, to some extent.
Yeah, and vice versa. I mean, there is a general trend in the universe that the complexity of the periodic table has been created in stars.
Yeah.
In fusion reaction in stars. So the universe started with the Big Bang, what we call the Big Bang, which is really a theory about the evolution after the Big Bang, not about the very moment of the Big Bang. This is often confused. But this theory tells us that at the very beginning only hydrogen and helium were formed, essentially. Yeah. So only the very lightest elements of the periodic table. And all other elements, the whole 92 stable and whatnot, unstable elements and isotopes, they were formed in stars later on. At least the vast majority of them.
Yeah.
So
based on that sort of what is present, you will be able to see sort of a time stamp.
Exactly. So you can say, okay, this is a metal poor star. It doesn't have very many of these metals, so it must be somewhat older. But in principle, you would like to turn this around and say, Look, this is the actual age of this star. This star is 8.8 billion years old. We can really put an age on it, a physical age, and there are ways of doing this. I mean, one way in principle that is unfortunately not vastly applicable to many stars is to actually use radioactive elements to age date them. It's a bit like what we would do on Earth.
Yeah, like carbon dating.
Yeah, like carbon dating, exactly. It's not carbon dating, it would be uranium dating or thorium dating, but yes, it's a similar technology. And this has been applied to certain stars. But there are other more indirect ways. And then if you know, okay, I have a data point here at the time when the galaxy was only 4 billion years old. Let's say 8.8 billion years ago or something like that. And that is really what we want to do. And this is what we now do on a very large scale with stellar surveys, which contain hundreds of thousands or even millions of stars.
Yeah.
And also the Gaia space mission, which gives us the distances to the stars, which is another important and very difficult measurement to make otherwise.
This was in relation to the Gaia Mission.
Yes, that's true.
The Gaia Mission is this very ambitious project from the European Space Agency that sent out this measuring
device. It's a couple of telescopes in principle,
and it was also having a spectrometer on board.
It does, yes.
To survey 1 billion stars.
Yeah, it's
and galaxies or just stars.
No, there is. We need the galaxies very crucially for the measurement because they serve as a reference frame against which the distances are measured. So Gaia is essentially. So it's a so-called astrometric mission, which means that it can measure parallax. It can measure how things change, how things change as the satellite changes perspective.
Yeah.
And the satellite goes around the sun together with the Earth, and thus changes perspective over the course of the year by some 300 million kilometers. And this is enough to measure distances throughout the galaxy, which is quite a fantastic thing. I mean, it's basic trigonometry. It's what you study in school.
Yeah.
You can draw these triangles, and then actually, if you can determine these small angles, you can measure the distances to stars. And that's fantastic. And then the galaxies are so far away that they don't show this effect. They don't show any change in angle, so we can measure the small angles that the stars
in relation to that.
In relation to the galaxies. Yeah. But the count currently is at 1.7 billion stars. So
1.7?
1.7, yeah. That's we didn't quite know how many stars we would observe when we send the space mission up.
But it sort of exceeded expectations.
It exceeded expectations, but we were wise enough to build instruments that were capable of also determining these parameters for that many stars, yes. So to put things in relation, 1.7 million stars is about 1% of all the stars in the Milky Way. So it's not a fantastically...
It's not a good population sample.
Oh wait, I mean that's another question. How many people do you interview when you want to sample the population? Well, typical numbers when people make these phone interviews is maybe, the typical number is 1001 actually. Yeah. And put that into relation to a population of maybe 10 million Swedes. Yeah. So 1% is quite sufficient to get a representative sample and that's the key thing with Gaia, if this measurement is not only local. Yeah. And Gaia actually measures about half of the Milky Way, so we get 1% dispersed across about half of the Milky Way.
That's really cool. So we actually get a representative sample of the Milky Way in relation to the Gaia's location, distance, and also gravities and
the rest is something that nature just provides. I mean that we still have to study. Yeah. And that tells us that those pieces of information encode again the evolution of the Milky Way as an example of the evolution of any grand spiral design galaxy in the universe, most likely.
But there you'd also be able to look at like what you're looking at, the composition.
To some extent, that's one of the things where Gaia is not cutting edge. So Gaia does some spectroscopy, but that's not the best spectroscopy we can do. We can do much better from the ground. Yeah. Not for hundreds of millions of stars at this stage, but we can do it for millions of stars. What we essentially want to do now in this coming decade is to look at the Gaia data, select stars that we think are interesting, Either we believe they are a good subsample, a good representative subsample, or they contain something new that we haven't found, and such stars we have also found. Actually, I can tell you more about this if you want to. And then we do spectroscopy from the ground. And then we can, as I said, have access to all these different elements. And there are different, what astronomers call nucleosynthetic channels, so different ways in which these elements are formed. So there are different groups of elements you want to sample and look at separately in order to understand how they were built up, and thus how the galaxy worked, because different elemental groups were built by different stars, and so then it tells you about the presence of these stars at a certain space and time, essentially. So that's an important realization, that science is no longer this sitting in an office with pen and paper and reinventing the world like Einstein did. I mean, literally, that's what he did. I think these days are over, most likely. Yeah. The revolutions that will come, and I'm sure. I mean, it depends on what you denote a revolution. Yeah. But there are things to be discovered. We know that the universe consists to 95% of things that we don't even know what they are. So that is something that we really have to put physics behind, and this is the holy grail in some sense. Yeah. So this will happen, but it will not happen, I don't think so, at least, by an individual coming up with a new theory. It'll be, there's plenty of theories out there. We just have to empirically confirm them. It is a human condition that we are curious about our surroundings, and we do that not just for the sake of quenching our curiosity, but also because we have to understand our surroundings to be able to cope with new situations. And we are waking up to this realization that the cosmos is not quite as benign as we would hope, and that there are actually perils out there that could impact life on Earth very severely. Let's talk about the extinction of the dinosaurs, for example, right? This is something that in principle we're not far from dealing with if we found out in time, and there are alert systems now in place to check that near Earth objects, as they are called, they're being monitored on a regular basis, so that nothing will happen. And you can take this to the next level. So that is asteroids in our own solar system. The next level would be to study how often our solar system, as an object that is a few 100,000 times the distance Earth-Sun across, how often this object encounters a nearby star, another star with the planetary system, and what consequence that may have. And it turns out, again, that's the latest numbers from the Gaia mission. These encounters are quite frequent. So it's not that they are, obviously they haven't been so severe that they have caused havoc in our planetary system. That would be disastrous. So we haven't experienced a close stellar encounter in the last 4.5 billion years, the age of the Sun and the solar system. But
that's up to luck, really.
Well, I mean, interstellar space is essentially empty, and stars are tiny objects. Solar systems are maybe not so tiny, but still, in comparison to the distances between stars, they're comparatively small. But then, as I said, we live in the spiral galaxy. There are many stars that orbit with us around the galactic center, but there are also relative motions between these stars, and this is what we study with Gaia. And we now find that these encounters are frequent. I mean, they happen, depending on exactly how you define such an encounter, every million years or so.
That's amazing.
And this tells us that, or what these encounters will do if they don't do something more severe, they will disturb the very outer parts of the solar system, what astronomers call the Oort Cloud, which is a reservoir of comets. So, and if their orbits are disturbed, some of them will be just sent into interstellar space, but some small fraction of them will also be sent towards the inner solar system. And these are then potentially hazardous objects for life on Earth.
And maybe in time, having a detailed map of the Milky Way will be really useful.
And it's not the final map. We're talking about people did arduously over many centuries with with continents of our planet to map out the contours of the coastlines.
Yeah.
Right? It took many centuries overall, and we're undergoing this process now with the galaxy in some sense. We're already planning the next Gaia mission, so to speak.
Yeah.
Whether it will happen in the 2040s or in the 2050s, nobody knows. But we know that if we want to advance on this at the same speed or asking similar science questions in the future, we will need another mission. Sort of around the middle of the century.
Yeah. And is that with different instruments or with the same sort of instruments?
So the current idea, it's a good question. The current idea is that we would do something very similar technology-wise, but where Gaia has not been able to deliver so well is precisely in the galactic plane, because there's too much gas and dust in the way, so we can't see very far in the plane. So for example, towards the galactic center, we can't see in the optical. Gaia measures optical light.
Yeah.
So the way to solve that problem is to build a Gaia spacecraft that essentially works in the infrared.
Yeah.
The infrared light is much better at penetrating dust.
Yeah.
So that is the way that we could look much deeper towards the galactic center. Scientists, I mean, it's not necessarily an easy life, right?
No.
In the way that the career is a very difficult. It's very intransparent how to make a career. The employment conditions are not necessarily very favorable. And sometimes very insecure. We got ourselves into this knowing this, so that's a choice. Of course, I'm not saying that I'm sacrificing my life for science, but I think many scientists are very committed to their work, just out of this internal motivation, this drive to understand and to make progress.
Should we let that be the last word?
We can do that. All right.
Thank you very much. And I'll add links and notes so people can find you.
Okay.
Thank you.
Thank you.
Bye.